Well, good morning, good afternoon, good evening, depending on where you are joining this session from. I want to say thank you so much for making out the time to attend this session. So we would be looking at this topic, which is managing a data analysis project. So just a little housekeeping. At the moment, you are all muted so that the session will go smoothly without interruption. The moment the session ends, I will open the room for you to ask your questions. But in the meantime, if you want to drop in the questions in the chat box, no problem. We will attend to them. However, because this webinar has very limited time, I would appreciate if the questions are focused on the webinar, but any other questions you may have outside the title for this particular webinar, we can discuss that offline. My contacts are on the slide, my emails are there. You can chat me up, then we can discuss it so that we would be able to take enough questions that are particular to this session because of the limited time that we'll have. So thank you, everyone, for joining. And just to confirm one last time, if you can hear me so I can progress. I don't want to take that for granted. Just one more time. Yes, okay, beautiful. So let us roll. So I would try as much as possible to ensure that this session is as practical as it can be. Could you also confirm you can see my slide? You can say yes in the chat box. You may not be able to speak. If you can see my slide, okay. All right, fantastic. Okay, so let's roll. We're good to go. So the title is Managing a Data Analysis Project, and I want to make it as practical as possible, because now we're in data analysis and I don't want to do the whole of the theory stuff and we just go. So it would be a bit practical, but I'm glad the session is recorded. So if there's a path you don't flow in terms of the analysis aspect, then you can refer back to the recording. I would be using XPSS, although there are many statistical softwares which you can see. I use several of them: Arrow, Epinfo, Stata, MATLAB. There are many of them, but just for the practical demonstration of this session, I'm going to be using SPSS. But it doesn't mean SPSS is superior than others. It's just what I want to use for this session. I am hoping those of you in the data science, the Auto8 Data Science Hub, you get regular info, because these trainings will, in terms of demonstrating practically how to use a statistical software, will come regularly. But that is not the purpose for this particular webinar. This particular webinar is just to show you I had a project and this is how I went about it, and this is how I was able to analyze the data based on the study objective of what we wanted to achieve. And before we dive in, I would like to thank Inaps and the Auto8 for supporting the Auto8 Data Science Hub, that is providing this session to you at no cost. So we go to our session. My name is Felix Emeka Anyem. My background is public health, epidemiology, biostatistics, and most recently, data science. Presently, I am a PhD fellow at the Durban University of Technology in South Africa, where I'm currently undergoing my PhD around the area of strategies to improve HIV self-testing amongst vulnerable populations. That is men who have sex with men, female sex workers, injection drug users, and the rest of them. So my details are here in case you want to reach me offline. So how do we begin the session? Now, managing data analysis projects is crucial for any success of any research endeavor. I mean, you have to agree with me. There's no, research, evidence-based research that you're going to do that will not involve a data analysis process. Although the data analysis I will be focusing for this webinar is the one for quantitative, but there are also data analysis for qualitative. For those of us that won't be using survey to collect raw data from participants or using online survey to collect data, but you will be using an audio recorder, get that data, and later analyze it thematically. My PhD, it's actually a mixed study where I'm doing both the quantitative and the qualitative. And sometimes you can actually do that, especially when you have a research title that you think the quantitative will not be able to address everything. Like if you see my PhD, I have the strategy aspect in it, and I'm using the demographic health survey data, which is the quantitative that did not capture very well the strategy aspect that will improve the HIV self-testing amongst vulnerable populations. So my supervisor, Professor Sibia and Professor Ladimeji, recommended that I have to add the qualitative aspect. So in the qualitative aspect, I interviewed female sex workers, brothel-based female sex workers. That way I was able to get robust content data on strategies they think would improve HIV, self-testing, which is different from going to the health facility to test. But this time you can actually stay at home or wherever you are and do the testing yourself. And that will help minimize stigma and all the restrictions that come from going to the health facility to test. So there are some instances where you can do mixed method, but for this webinar, I am focusing on quantitative, examples. So whatever research you're doing, the data analysis plays a key role. That's why it's an aspect you have to take very, very seriously. Especially in your career, you have to try as much as possible, to build a skill in this area, which is what the Auto 8 Data Science Hub is trying to do. We're trying to see how we can build a lot of skills of researchers in the data analysis, platform. So one thing you also have to appreciate that the data analysis also comes with a good project planning, clear communication, efficient data management, and quality assurance, among other things. So I will discuss some of the projects I have been in, and you will see how I navigated the process. Like I said, this would be more practical, then you can ask your questions later on. So this is one of my quotes that I love so much. Richard Fisher is one of the fathers of statistics, and it's someone that I learn a lot from. You've heard of the Fisher's exact test and many other, statistical tests. And this is a quote he used. It says, to consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. So what he meant is, you don't wait until your data is collected before you consult a statistician. You consult a statistician from the beginning of the project. They have to plan with you, because you know that it's not only about analyzing the data. There are many other aspects that come before the data is even collected. Planning the methodology itself, the study area, the sampling process, the sample size, all those issues, the statisticians help you solve them. So when, after you've collected the data, you now find a statistician, you now begin to find loopholes. And what are those loopholes? For example, you said you're going to do this, and what you say you're going to do, which is part of your study objective, is not in the data that you collected. So at the end of the day, you find out that the data that you collected is not able to answer your study objective. And this can only happen because you didn't seek a statistician. You just went ahead to design your tool. And you're thinking that somehow, the data you've collected will be able to answer your study objective. So you need to pay attention to these things, because if you go to the field and collect your data, and at the end of the day, that data is not able to answer your study objective, the only option, my dear, is to go back to the field and collect the data the second time. I mean, I've seen students make this mistake. That's why I always recommend to always work with a statistician, a data analyst from the beginning, so that they can actually guide you. And this is what Richard Fisher recommended. So this is the first project we would look at, which is a cross-sectional study of coronavirus disease prevention practices among university staff and students in Durban, South Africa in 2020 to 2021. So this work was done in my university in South Africa, and it was pioneered by my supervisors, and I was brought in to also engage in the project as a statistician. All right. If you look at this title, however, it is clear that the study design is a cross-sectional study just by looking at the title. Okay, but it's not all projects, that you may have a clue from the beginning what the study design would be, but it is clear in this title that it's a cross-sectional study design. So that part is already settled, because we had initially planned, what this work or what this project would be in terms of what the study design would be. Yeah, I am using full screen on the slide, so you may need to check if you're using your phone or something, but the slide is full screen. Please, can we all confirm the slide is full screen? Maybe I may need to stop and reshare. Is the slide full screen? You can say yes or no if the slide is not full screen, so I can reshare. Okay. 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 So most people have confirmed that the slide is full screen. Okay. All right. So let us progress then. You may need to check your device. Thank you. So we would progress to the next slide, and you have to appreciate that we had a timeline for this project, and that was in the heat of the coronavirus. I just left, it will interest you to know that I just left Cape Town like few days before the lockdown, back to Nigeria, and it was, quite interesting, but I did most of the data analysis, from home in Nigeria. So the first thing you do when you're planning a project is you have to be clear on the purpose of that project. What exactly do you want to do? A project always have an aim, one thing it wants to achieve. It can have different specific objectives, yes, but it will always have one aim. Because having the study aim, the project aim guides you. It guides you very, very well. I remember a few years ago when I, defended my my thesis in my second master's in public health. I defended it at my local university, at the University of Port Harcourt. We had a meeting, so my thesis was accepted for presentation. And in my second master's, I worked on the prevalence of noise-induced hearing loss amongst musicians, those that play musical instruments for churches. And it was quite an interesting study, because I saw a lot of determining factor, that could make musicians susceptible to noise-induced hearing loss. But I focused on religious houses, especially churches, and when I finished presenting, one of the attendees asked me a question. He said, it is not only in churches that you have issues with loud sound. You also have issues with loud sound in clubhouses. You also have issues with loud sound in mosques. You also have issues with loud sound in many other places at the airport and the rest of them. So why did I only do for, churches? And I answered that that is the scope and the focus of my research. This is what I have decided to do. Because when you're doing a research, you can't be a unicorn. You can't be everywhere. You can't do everything. It's a research. You pick one area, you focus on it, and you achieve it. So if someone has read my work and is inspired and say, wow, this work is interesting, I think I will duplicate it in the clubhouses. I think I will duplicate it in the airport. I mean, go ahead. That's why it's research. You don't say, oh, I think there's noise everywhere, so let me focus everywhere. No, you can't be a unicorn when you're doing a research. It causes a problem for you because you will never finish that study. And you may not have the funding you need to actually achieve that. So you pick a scope, you pick an aim, an objective, what you want to achieve, and you get to it and achieve it and you move on. So in this study, we focused on preventive practices. There are many other things about COVID-19. There are many things, but we say, oh, we want to focus on preventive practices and the associated factors, and that's it. And it was published. You don't say, oh, it's not only preventive, there are many other things. No, leave other things for other researchers to do. Focus on something that you can achieve in the shortest possible time and with the availability of the funding that you have. So that's how it is. You have to understand your project scope and objective. And a lot of researchers fall into this trap. That's why they never get their project completed. Because you want to do something and someone say, oh, I thought about this, add it. Oh, I thought about this, add it. Before you know what is happening, your project is a unicorn. It's not focused. You don't have a clear direction. And the danger is it will be difficult to actually get it completed. So please try to run away from that temptation. For the meaning of cross-sectional study, I'm going to explain that further as we go on. To join the AutoAid Hub, I would share the link later on. Please remind me. Thank you. So we move to the next slide. You have to assemble a team with clear roles and responsibilities. It's not everybody you bring into your team. You bring people that are ready to work. People you know that have the expertise in that particular field to carry out that research. So this research was driven by my main supervisor here, Professor Sibia, my main supervisor, Professor Oladimeji, my co-supervisor, Professor Sibia, and Dr. Kelechi. These were the three key teams. Then I was brought in as their student and also the data analyst. And if you look down here, you would see that we all had aspects that we contributed. Everyone had an aspect they contributed. This has been a danger for a lot of researchers. You're carrying out a study and a lot of people are pleading with you, oh, add my name, oh, bring me in. And you know very well that these people have nothing to offer. And they keep dragging your project, At the end of the day, you get frustrated. Please, when you are conceptualizing a project, bring people you know can add meaningful contribution to your project. Don't bring people out of sentiment. This is not a political party. I want to do you a favor. This is research that will inform policy, that will save people's lives. So don't be political about it. Do your homework. Is this team, is this person going to contribute meaningfully to this project? If they are not, take their name out. There's no sentiment. The day you have a project they can contribute meaningfully, you bring them in. select your team carefully, because everyone is going to play a role. Not at the end of the day, you begin to get frustrated. You're the only one writing everything. You're the only one doing everything. And you're like, my team, what are you people doing? Because you didn't take time to assemble your team. Check their track record. Ensure they have what it takes to work with you and get your project done. There's no project that is meant to be eternal. It has timelines, and that timelines has to be met, especially when you have a funded project where the funding has timeline. And you have to appreciate the fact that if you don't get your project completed in that timeline, you don't get extra money for the extra months that is taking you to complete that project. So think about your team very carefully and what each one is going to do, their responsibilities. Don't say, oh, I'm going to bring you in later, I'll figure out what you will do. Ensure that is sorted out from the beginning. Now, structure your data collection to align with your study aim and purpose. I mentioned this initially. Our goal for this project is to investigate the COVID-19 preventive practices. And apart from the social, this is like an excerpt of our questionnaire. Apart from the section A, which is the demographic characteristics, that one is clear. I mean, every questionnaire has to have a demographic characteristics because demographic characteristics can influence dependent variables. So you have to ensure that they are not adding more weight on your study outcome, in our case, preventive practices, than it should be, because you have to do what they call the multivariate analysis to test for confounders. I'm going to explain that more as we go. So section A is by default, social demographic characteristics, the age, educational level, occupation, the rest of them. Then you have to ensure that you add your dependent variable. Your key outcome, in our own case, is preventive practices. It's actually in section C, preventive practices. All right? Because it doesn't make sense you design your questionnaire tool and your main outcome is not in your tool. This is where you need the assistance of a statistician, because they have to look at your study objective and look at your tool side by side to ensure that all the study aim and the specific objectives you want to answer, they are all incorporated in your questionnaire or your study tool. So that at the end of the day, you won't collect the data and now realize that some of your aim or your specific objective are not captured in your tool. There's only one solution to that. Going back to the field, redesigning the tool, incorporating them and recollecting the data. And that can be a very tiring and expensive process. So please ensure you don't fall victim to this. Don't be carried away by your project. Don't be so excited, that you don't consult those that you need to consult. Don't be in a hurry to collect your data. That's why we do what they call pilot tests. Why do we do pilot tests? It's so that you can be able to pilot that too. So if your sample size is like the usual recommendation is usually 20% of your sample size, population for that research. Probably your sample size determination number, the minimum sample size for the project that you calculated is 200. You can pilot that tool with 20% in a different population. Like in this case, we're doing a study at Durban University. We can pilot it in another university, maybe Cape Town, or Johannesburg, a different university. That pilot will help you because the people you're giving this tool will be asking you questions. Say, I'm not clear on this question. This question you're asking is not clear. That way, it helps you go back and revise your tool. You give the statistician the pilot to analyze. That way, he begins to tell you, oh, I think you didn't capture this. Oh, I think you didn't capture this. This is part of your objective, but from the analysis, it's not there. That's why pilot is good before you can administer the main study tool. So define the methodology of your study. You have to define your study site. Where do you want to collect that data? You can't collect data from everywhere. Can't collect data from everywhere. You have to decide the region. unless you're using a demographic health survey. Like in my own case, for my quantitative, for my PhD, I'm using a demographic health survey. And that demographic health survey that I'm using is from 38 African countries. So I have pulled the data together of 38 African countries, very big data, over 500 something thousand participants that were eligible to be included in the data analysis. Quite a very large, robust data analysis process. Yes, unless you're using a DHS, but if it's not a DHS data, you have to decide a study site, a particular place where you want to collect that data. So in our own case, our focus was on the Durban University of Technology. Our focus is students and staff on campus, and your study design have to be clear. In our own case, it's a cross-sectional study design. And someone was asking, what is a cross-sectional study design? I'm going to explain that, then we will go back. Now, a cross-sectional study design is a study design where you want to determine prevalence. Anytime you're doing a study and you want to determine prevalence of your study, prevalence of something, prevalence of the outcome, it's an automatic cross-sectional study, because in a cross-sectional study, you always have the exposed group and the outcome in the same population. Like in our own case, the exposed group are those exposed to COVID-19. Then the outcome is those that have good or poor preventive practices. So both the exposed group and the outcome we are looking for, they are both in the population. So in the population of those that are exposed to COVID-19, we get our outcome from there, those that have good or poor practices to COVID-19, so that makes it a cross-section, because you take a cross-section of the exposed group and you get the number of those that have the outcome in that exposed group. That's why it's a cross-sectional study. So most prevalence studies are cross-sectional study. Anytime you're doing a study, you want to check prevalence of good preventive practices, prevalence of noise-induced hearing loss, prevalence of malaria, any prevalence study, most of the time and all of the time, they are cross-sectional studies, because you are going to a group that is exposed, and in that exposed, you want to check the number that have the outcome that you are interested in. That's a cross-sectional study design. But there are other study designs like the case control and the cohort and the experimental study. So we did a cross-sectional study because we are looking for the prevalence of those that have good preventive practices of COVID-19. Our population was clear, students and staff. Like my population was clear in my master's, where I'm focusing on those that play musical instruments, and in our own case, we did a convenient sampling for this particular study because we sampled everyone on campus, all the staff and all the students. So there's no need for a sampling method here because you're using the entire population. That is not usually the norm because it can be expensive, but in a case where you're using everyone in that population, then you don't need a sampling method per se. It would be convenient because you're using everybody. But you can't do convenient sampling where you want to pick a subset of the population from the entire population. That will introduce sampling error in your work, because that way you are not giving everyone an equal chance of being selected. So you have to be careful how you sample your product. And when you're talking about sampling, it can be probability and non-probability sampling. In our case, we did non-probability, which is a sampling framing in the sense that you have to have a list of all the eligible people for that study. So if you've calculated minimum sample size of 200, then from that list of all that are eligible to be included, you put their name in a paper, you put it in a bowl or in a box, you shovel it, and you pick the number that you need. The 200 that you need from that pool, which could be 3,000, which could be 2,000, which could be 1,000. So that is random sampling, meaning everyone that is eligible makes your sampling frame. Then from that sampling frame, you randomly pick the number you need. That's simple random sampling. Stratified sampling comes in when you may fall risks of picking more group than another, especially when in that population, they have more people in one group over the other. A very good example is the military. If you want to do a study, especially in Nigeria, there are some countries where they have a lot of females in the military too. But in Nigeria, we have more males in the military than we have females. So if I want to do a study, like a prevalence of malaria, for example, and I go to the army barracks and I do a random sampling amongst the people living in the barracks, you find out that for every 20 males that I sample, there may be one female. So you find out that your data will be skewed, favoring the males more than the females. So any association you do will look like it's all favoring the males or favoring the males. So in a case where you have one group having more population than the other, you have to do stratified sampling, meaning that you have to take all the males to one group and all the females to one group. So if your sample size is 200 to take from that population, then you have to take maybe the 2,000 military males or the 3,000 military males will be on one side. Then the 300 or the 400 or the 500 military females will be on the other side. Then using simple random sampling, after you've stratified them, you can now use simple random sampling to pick the number of males you need, 100, the number of females you need, 100. That way you have a balanced population between the male military and the female military. Because if you don't do that, you will have more males than females. Another example is when you're doing a study where you want to look at associated factors of vagina and cesarean section delivery. You have to do the same, because if you do simple random sampling in the population of women that live in the hospital, you will get more vaginal delivery than cesarean section. So the cesarean section one side, vaginal delivery one side, and you pick the number you need in both sides. Stratified comes in. The other one is cluster sampling, so that you don't bear the brunt of a large population. So cluster sampling means when you're doing a study where the cluster too many. For example, you're doing a study where you want to focus on public primary school. In your city, you can have more than 1,000 public primary schools. So how do you take a sample from 1,000 public primary schools? That's a lot of work. It may not be achievable. So you can cluster sampling to identify each public primary school as a cluster. So using simple random sampling, you can pick 5, you can pick 10, you can pick 20, depending on the number of public primary schools that can achieve your sample size. So that's cluster sampling is allowed. So each of the school can be a cluster. Each of the club can be a cluster. Each of the religious house can be a cluster. Then you can pick the number that you need. You don't have to do a sample of all of them. So that's where cluster sampling. Once you identify them as cluster, you can now use simple random sampling to pick the number you need. So these are the basic, sampling method. But in our own case, we did the convenient sampling because we were using everyone. In our data collection, we did an online, we used the Google form. A lot of us are familiar with the Google form. It has the capacity to also generate an Excel sheet. So if you look at this link, the Google form could look this way. Okay, this is so when you design the Google form, okay, it will look this way. All right, so participants can actually fill the Google form for you. Because in our own case, we have to use Google form because it's not easy to reach all staff and students in the university. There are so many of them. So we design a Google form like this. Then when they fill the Google form, it comes here, responses. So you'll be able to track how many persons are in the Google form. So sometimes if you're not getting enough, you can send reminders. So once data completion is end, it's easy to access this. You just go to the responses. You will see the link to Excel sheets. So the link to your Excel sheets is here. So you just come at these 3 dots here. You click on that 3 dots. And what do? You download the responses. So once you click it, that responses, it's going to download. And it's going to download as a CSV file. And that CSV file, if you open the CSV file, it's a form of an Excel file. See it here. It's a form of an Excel file that you can now use to import in your XPSS or Stata or EpiInfo or SAS or whatever statistical software you are using. That is what we did basically. We actually used online data collection too. Some persons will use physical questionnaire, all right? And we use the SPSS statistical package to run the data analysis, which I'll show you a bit of what I did. So I've talked about this. I've talked about this. Now, the data collection tool may not only be Google form. There are many ways to collect your data. Questionnaire, SurveyMonkey, Quadrix, one of our projects that we did with the University of Toronto that funds by Center for Health and Development, we used Quadrix. We didn't use Google form. They were more comfortable with using Quadrix. You know, Typeform is there, Microsoft Form is there, Zoho Survey. So there are many of them. There's a present study that is ongoing. It's a clinical trial we're doing in 4 states. Rivers State is one of the centers. We have Kwara, we have Lagos, and Kano. So I am the data officer for Rivers State. So we're actually using RedCap to collect that data. So it depends on the project. The project will determine what form of data collection tool that you want to use, all right? So the data analysis now, what did I do in this project? We had 2 forms of data analysis. We did the descriptive statistics, then we did the inferential statistics. The descriptive statistics is basically describing the data. This is just it. You just describe the data, nothing much. This is what descriptive statistics is all about. You just tell us the variables you used. In our own case, for our demographic variables, we use sex, we used age, we used marital status, we used level of education and many others. So these were our demographics. Sometimes it's called social demographic, sometimes it's called demographic. It doesn't really matter, you know, whatever words you use. And at the end of the day, we had about 5,849 students and staff, you know, that responded to this survey. So it's actually a very encouraging number, you know, for a survey of. So you can see we did, like, for the categorical data like the male, female, you know, we got the frequency, we got the percentage. For age, which was also categorized, for those that are between 17 to 26, we have 4,729 persons respond, and this was the frequency 80.85. Now, some persons may wonder, how did you get this 80.85? It's easy, although the statistical software generates that for you. But to get a percentage, it's easy. You do 4,729 times 100 divide by the population. So 4,729 times 100 divide by 5,849, which is the population, will give you 80.85. So that's how the population is generated. But the statistical software does that for you. Then for the continuous, for the raw age, because they also gave their raw age, I did an average. So you can see that majority of the participants are around 24 years old, because this is a school. So you understand, why you would have very young people in this survey, and you would understand why you have many single people because it's a university, and you can understand why you have many tertiary people because it's actually a university. All right, so this is what the descriptive statistics look like. You just describe the data in terms of frequency and percentages. Okay, so for the descriptive statistics, what did I really do? But first of all, let me show you the main dependent variable, which is this. It was also described. The main dependent variable is the preventive practices of COVID-19 transmission. This is what we want to find out. So for those that have good and adequate preventive practices, which is a score 6 to 9, we had more. So majority of the students and staff had a very good and adequate preventive practices, while only 6.21% had poor preventive practices. So this is our main outcome. So no matter what we do in the statistical analysis, if we're not able to achieve our main aim of the study, then that whole project is defeated. So we're able to achieve this. So it is this outcome we will now be able to use for the inferential statistics to check the independent variables, which are these independent variables, how they are associated with the main outcome variable, which is the preventive practices. So before I move to the inferential, I want us to take a look at the data itself. So this is the data, because we collected it online and we downloaded it, and this is what it looked like. So the position, which is full staff, contract staff, and students. All right, so for those that are both staff and students, we call them both. We have students, we have staff. So this is the position for students and staff. And what I also did was, when you're going to run bivariant logistic regression, you need to turn these values into numbers. But if you're going to run descriptive statistics, maybe inferential statistics like chi-square, you don't need to turn them into numbers. But if you want to run logistic regression, bivariant logistic regression, and multivariant logistic regression, you have to turn these into numbers. Now, what numbers you turn them into is at your discretion. But you have to know what is 1, what is 2, what is 3. That's why after every variable here, you would see I've turned it into numbers, because I also want to use this variable for logistic regression, and I called it L arrow. All right, the gender is there. We have the age, the raw age, where I'm going to use, which I'm going to use to get the mean and standard deviation. I have my age, which I grouped into 3, and I have another age group, which I grouped into 6. Then I have the age group that I want to use for the logistic regression, which I've numbered. All right, I have my marital status. Then down here, I have the main outcome, which is the preventive practices. Now, for the preventive practices, this is a bit tricky, because you can't get preventive practices just by asking someone, do you have good prevention practices of COVID-19? Of course, everyone is going to tell you yes. So you won't ask them that sort of question. What you do is you have to devise different questions that you ask them. At the end of the day, you have to group and be able to tell whether they have good practice or poor practice, which is what we did. So we had 9 questions. So these 9 questions were asked. Now, the first question, as you can see, is we asked, in recent days, have you gone to any crowded place? If someone says they've gone to a crowded place, which is yes, definitely that means they have poor preventive practice. During the COVID-19, you are not supposed to visit or go to a crowded place. So if someone says yes, they've been to a crowded place, it means they have poor. And from my methodology, which I'll show you in the slide, you would see that what I did was, all those that have good were scored 1. All those that have poor were scored 0. That is what I did. All right? Because there are 9 questions. So at the end of the day, I added, if you score between 6 to 9, you have good. If you score less than or equal to 5, you have poor. So you have 9 questions, you just divide it into 2. If you have 10, it's the same thing. If you have 20, it may be less than or equal to 10. So you just divide it into 2. Less than the 50% is poor, and greater is good. All right, so that is what I did. So if we go back to the Excel sheet, you will see that if someone says they go to crowded places, this is poor practice, they're going to have 0. All right, so if you look at the practice, the sheet that I used to actually turn this yes and no into 1 and 0, depending on good practice or poor practice. So if you look at this first one, which is yes, it will probably be 0 in my scaling. So if you come here, you see it will be 0 because the person says yes, which is poor practice. The next question is 0, which is poor practice because the person also said yes. If you said no to going to crowded places, that's good practice. If you check here, that would be 1 point. So at the end of the day, I have to add all the 9 questions. So those that have 6 and above, all right, meaning 6 to 9, they are good. Then anything less than that, 5 and below, they are poor. So that is how I did the scoring for good and poor. Then for my regression analysis, our interest is in the good, because for your outcome variable, you have to decide which value you are interested in. So for this analysis, we're interested in those that have good practice. We want to see predictors of good preventive practices. So the value you're interested in, your main outcome should be 1. Then the value you're not interested in should be 0, which is what I did. If you want to put it in logistic regression, which I'm going to show you. So good preventive practice, that is our interest. So it is 1. Poor preventive practice, that's not our interest. So it is 0. So I've already done all these categories, before I move them to the main, data sheet here, which is 1 and 0, depending on whether they have good practice or poor practice. So this is what my data looks like. So first, let's do an analysis of the descriptive statistics. So this is my SPSS. So if you're using XPSS, to load that data, it's very easy to do. So how do you load the data? You go to the folder, you click on that folder. If you see here, which it says file type, SPSS, the file type is not XPSS. I'm using Excel sheet because the data it's an online data downloaded through CVS, which is a form of Excel sheet. So I'm going to change this file type to Excel because that is what I'm using, Excel. So that data is saved in my desktop. So I'm going to go to my desktop where that data is saved inside this webinar practice data folder. That's where I saved it. So this is the data, DUT COVID-19 knowledge and practice study. So that's it. So once you select the data, you just say open. Once you say open, it's going to show you this, telling you that all the variables in the first row will be your key variable names. It's usually checked by default, meaning that in the Excel sheet, the first row has your variable name, the age, the marital status, and the rest, and you say, yes, I want the first row to be my variable name, which is what you did, or what I did, sorry about that. So it is checked by default, and you said, okay, that's all. Then the data will be loaded. So this is the data from the Excel sheet. It is already loaded in my SPSS. So I can now run the descriptive statistics that you saw, which is easy to run. So once your data is loaded, you can run the descriptive statistics. For the variables, that have the outcomes you can see. The one that has the numbers, I want to use them for the logistic regression, so I'm not going to run that. So to run the descriptive, you just go to Analyze, Descriptive Statistics, then you go to Frequencies, because that's what I want to run. So I want to run frequencies. Then here, it checks by default, display frequency tables by default. So you just leave it. If you're going to be running frequency and percentages, you leave this checked. So I want to run position. Once you check, highlight it, you push it in the variable line, maybe gender, maybe the age group, all your categorical variable, you can put them now, marital status. You can put your education inside. Then you can put your main outcome, which is the preventive practices. You can click it, then you can put it there. So once you're done, that's all you do for the frequency and percentages. You don't do any other thing. Once you move the data from here into your variables, and this is checked, you just said, okay. Once you say, okay, this is it, it displays your variable name, the frequency, the percentage, and the valid percent. Now, you don't use the valid percent, you don't use the cumulative percent unless you have missing data. If you have missing data, then you're going to be using the valid percentage, because if you have missing data, your percent will add a percentage to that missing data, and that's not accurate. Your missing data is not supposed to have a percentage assigned to it. So if you have a missing data that has the number of the missing data, that has a percent assigned to that missing data, then you have to use valid percent, because the valid percent will be the accurate percent, because it's not going to attach any percentage to the missing data. But peradventure you don't have a missing data, fine. You're going to be using frequency and percentages. So this is how it's done. So this is the position. This is the gender. Female, 3,351. The percentage is 57.3. So this is how I calculated my descriptive statistics. But you're not going to be using the table generated by your SPSS in your work. I see students do that. It's not allowed. Once the statistical software gives you an output of your analysis, please design your own table and move the values. Don't copy. You can actually copy this, right-click copy, and paste it in your Word document. Please don't copy your analysis output and put in your Word document. Create a fine table like what I've done, like this. Move those values into this table. This is what we want to see, not the statistical analysis output. All right, so this is how I was able to analyze the frequency, analyze the percentages. All right, and also for my outcome too. I created a table for that. So that's how I did my descriptive statistics. So what about the inferential statistics? The inferential statistic comes in when you want to do associations. You want to check how your independent variables, are associating with your dependent variable or your treatment group in terms of randomized control trial. In my own case, my dependent variable is the preventive, practices of COVID-19. So I want to see how the demographics associate with them. What age group, what gender or marital status, associate more in the dependent variable, all right, for my inferential statistics. But before I go to inferential statistics, I forgot to show you how to do the mean and standard deviation for like continuous data. So if you have a continuous data and you want to run the descriptive for them, it's a different process. How do you do it? You go to analyze, you go to the same descriptive, you go to analyze, you go to the same descriptive, frequency, you have to reset to bring all this back. So you reset, you bring all this back, then you can now pick your age. You can see the ladder sign here to show you that it's actually a continuous variable. These ones that have the ball signs are categorical in XPSS. This ladder sign tells you it's a continuous variable, like a ladder that has no end. So you put it inside the variable line, but you have to uncheck this because you don't want it to display frequency age, because displaying frequency for continuous variable doesn't make sense. Let me show you what I mean. I mean, if you display frequency for age, this is what it looks like. It's so long, and you're not going to put this in your table. Those that are 17 years is 80, those that are 18 years is 384. I mean, it's too much. So for continuous data, we just do means and standard deviation, maybe minimum and maximum. Okay, so you go to analyze descriptive statistics, your frequency, and you uncheck this. You just uncheck it. It says you're turning off the frequency output. He said yes. So you go to statistics, it's like a buffet. It gives you so many things. What you need is probably your mean, your standard deviation, and maybe if you want to know the minimum and the maximum, you can check that. And that's all you need in that many things. All right. There are other times you may need median and interquartile percentiles. All right. But in this case, it's just the mean and standard deviation, maybe the minimum and maximum. Once you're done, you just continue and you say, okay. And that's how my mean and standard deviations were generated. That's how I generated them. So if you look at my Excel sheet here, my data, you will see the mean and the standard deviation, 23.67 and 6.47. If you check, is the same thing with what is here. All right, that's how I actually generated the mean and standard deviation that is on this slide. So for continuous data, for the descriptive is the mean and the standard deviation. All right, but if your data is skewed, then it means you may probably be using median and interquartile range. So we go back to differential statistics like I was explaining. Here, you want to look at associations. Yes, the slides will be shared and the recording too as well. So here you're looking at associations. So inferential statistics, whatever inferential statistics you use will depend on what you want to do, because there are many inferential statistics. There are many tests of associations, many, but in our own case, for this particular project, we did bivariate and multivariate logistic regression. We wanted to look at the odds of the independent variable influencing the dependent variable, which is our preventive measures of COVID-19. But there are many that you can do. Like if we want to test differences in means, like two means, like we want to test for how the age differ in the preventive practices. We want to see which age group, have better preventive practices. We can use the student t-test, all right, because we want to check differences in two means. If you want to check differences in three or more means, we will probably use the ANOVA, which is for the parametric, where you use the systematic process of selecting your sample, random, stratified, or cluster. But if it's convenient sampling, then you're going to be using the non-parametric, where you'll be using Mann-Whitney if you're comparing two medians, Kruskal-Wallis if you're comparing three or more medians. But in a case where you want to test for differences in proportions, you're going to be using the chi-square. But where that testing you're done or that proportion you're done, and there's a value there less than 5, then you're going to be using the Fisher's exact and not the chi-square, meaning one of the numbers there are less than 5 in your association of the differences in percentages of proportion. In a case where you want to check for differences in continuous variable, like the age or weight, if the age is increasing, is the weight also increasing? That's where you use the Pearson's correlational coefficient. But if it's an ordinal variable, like in a Likert scale where you have agree, disagree, there's an increasing order, strongly disagree, or the rest. For Likert scale, association of orderly variables, you're going to be using the Spearman's rule. But for this project, we use the bivariant and the multivariate logistic regression, which is recommended for cross-sectional and case control studies. But if your study is a cohort study simply means you expose them and you follow them over time, whether they will develop the outcome based on that exposure. For a cohort study, you're going to be using relative risk, not odds ratio that is generated when you use bivariant logistic regression. Yes, if your data is skewed, you're going to be using median. For example, you did convenient sampling. You didn't do systematic sampling. So if you choose anybody you like, your data is already skewed. So in those kind of data, you do non-parametric, where you be comparing medians, Mann-Whitney, 2 medians, 3 or more medians, Kruskal-Wallis. Yes, you're not going to be using means, because means are for data that are normally distributed, data that you selected. Your sampling process has a probability form, systematic process of selecting them. All right. So in our own case, we did bivariant and multivariant, which I'm going to be showing you how I did that. All right. So for the inferential statistics, you can see I already have my outcome, level of preventive practices, good and poor, which is my outcome. You have to know that for you to do bivariate logistic regression, your outcome has to be 2. You can't have 3 outcomes. Your outcome variable or your dependent variable have to have 2 groups. Yes or no, poor or good, or whatever it is. Treatment, no treatment. It can't be more than 2 groups. But your independent variable, which is at this side, can be more. It doesn't have to be 2. But if you put your independent variables here, then you have to choose a reference value, meaning that that value that will not have odds ratio that you're going to be making reference to. So one of that value has to be the reference value. All right. And how is odds ratios interpreted? If your odds is less than 1, it means it is lower odds. But you have to ensure the p-value is statistically significant before you can actually talk about it. So for the current position, we can see that our p-value is not significant because they are all greater than 0.05, which is the cutoff. So I am not even going to be talking about current position if being a student, a staff, or being both can have an influence on your level of preventive practices. I'm not interested in it because there is no significant difference. So I'm going to be skipping this, all right? But if you look at sex, male and female, you can see there's a significant difference, all right? So you can see a lower odds because it is less than 1. There's a lower odds and it's significant. So whether you're a male or female, you're a male or female, the good or adequate preventive practices have a lower odds compared to those that signified others. If you look at the age group, you can see the age group, those that are lower, 17 to 26, which is my reference group. But you can see something is happening in the age group. The odds is increasing as the age of the people are increasing. And it's understandable because the way the COVID-19 came up, we're told that the older you get, the more you have to take your health very seriously. So I guess that's why those that are older have a higher odds. You can see those that are between 27 to 36, they are 13.89 times more likely to have good or adequate preventive practices compared to those that are younger in age, which is our reference value. So whatever odds you get here, you make a reference to your reference value. You will decide what the reference value is when you're running your bivariate logistic regression. You can decide that your reference value can be the first or the last, but you can't choose the middle. That's how the statistical software works. Your reference value can either be the first or be the last. So in my own case, I choose the first to be my reference value so that whatever odds ratio I have, I will make reference to the first. So you can see in those that are between 37 to 46, they are 22 times more at odds or more likely to have good and adequate preventive practices compared to those that are younger. So you can see that as the age group is increasing, the odds of preventive practices, it's also increasing. All right, so that is what is happening here, which is the part of the inferential statistics which we did. So our level of practice is dichotomized into good and poor. For the good, we called it 1. For the poor, we called it 0. Like I said, before you put it in your logistic regression, you have to decide which value you're interested in. In this study, we're interested in good. So that value you're interested in will be 1. The other value will be 0. But for your independent variable, you're going to be listing them based on the order. So if I'm going to be aligning it this way, then both will be 1, student will be 2, staff will be 3. Others will be 1, male will be 2, female will be 3. Age, 17 to 26 will be 1, 27, 36 will be 2, like that. So you have to arrange it in that order so that if you're going to be choosing first as your reference value or last as your reference value, everything is orderly. So how did I do the bivariate logistic regression? That was very easy to do. So if we go back to our SPSS, this is our value. For the logistic regression, we're going to be using those that I highlighted LR because they are the numbers, because you have to turn them into numbers to be able to do your bivariate logistic regression. So how did I do that? I went to analyze, then I went to regression, then binary logistic, because that's the first one we did, bivariate logistic regression. Then the variables that are significant in your bivariate logistic regression, you put them inside your multivariate. So I choose my binary logistic, which is this one. Then the dependent variable is your preventive practices, which is this one, PP. All right, so you put it there, which is your dependent. It's only one dependent. So in our own case, 1 is good, 0 is poor. So now you can now choose your independent variable because it's bivariate logistic regression. So you choose the independent variable one at a time. You don't put all of them together. So let's look at the position. So I choose the position and I put it here. So that position, if you look at my slide, you will see that both, which is number 1, is my reference value. So my reference value should be the first. So if I go back to my SPSS, I have to click category so that I can make 1 as my reference value. So I click category and it's already here. So I click on it and I have to choose first. So meaning I want the first value to be my reference value. All right. Then once you choose that, you say continue and you now come here to choose the 95% confidence interval, because you need your odds ratios to have a 95% confidence interval. Then you say continue, and that's all you do. Then you say okay. This is the interpretation. See it here. So at the end of the day, you will see that the first, which is the others, doesn't have a number. The exponential B, that's your odds ratio. XPSS calls odds ratio exponential B. This is the significant value. So you can see for the first one, which is this, the first one, which is our reference value, does not have any odds ratio. The second one, which is our male, is 0.774. That's our odds. This is the 95% confidence interval. This is the p-value, which is 0.709. So you're using exponential B, which is your odds ratio, the 95% confidence interval, and your significant value. So those are the 3 things you need from this data. If you look at the table, that is what I did. You can see this is the male, this is the odds. The female, this is the odds. I'm looking at the current position. This is the odds, 0.774. If you look at the SPSS, you will see there's 0.774. That's the odds. The confidence interval is 0.20 to 2.90, the same thing that is here. You see it? That's what I did. The odds for female, for staff, is 0.55. That is what is here. 0.55. This is the confidence interval. This is the significant value. So you can see that it was not significant. After that, I did the bivariate for sex. Others is 1, male is 2, female is 3. And my reference value is 1, which is others, and it's significant. So how did I do that? You still go back to your analyze, regression, binary logistic. You have to remove this. You are done with position, you click on it and you remove it. You can now bring in your gender into this part. Then you have to choose the category compulsorily, because you have to decide whether you highlight it, you have to decide whether it's last or first. If you look at this table, you can see my reference value is first. So I have to, in the analysis, I have to indicate first is my reference value. You have to continue. Then you come to options to highlight your 95% confidence interval. If you've not already done so, then you continue. That's it. Then you say, okay. Then you go down the last table. That's what you really need. This is it. So you can see that for gender, the odds for the male is 0.099. This is the 95% confidence interval here, 0.018 and 0.544. This is the significant value, 0.008. The same thing with the female, 0.558. This is the confidence interval. This is the significance. So that is what I did for the bivariant. You have to do it one after the other. Once you're done with the bivariant, then the values that are significant in the bivariant, you will now put them in the multivariant. You will see that in this multivariant logistic regression, you will not find current position anymore because it was not significant. So those that are not significant, you will not put them in the multivariant. So it's only those variables that are significant in the bivariant, you put them in the multivariant. Why are you doing so? You want to ensure that the gender, age, marital status are standing on their own. They are independent. If they were significant in the bivariant and in the multivariant, they are not significant, it tells you that they are not independent, meaning that gender could have been influenced by current position, could have been influenced by age, could have been influenced by marital status. Why we do multivariate logistic regression is to ensure that gender is independent, meaning that it is significant on its own. Age is significant on its own. Marital status is significant, meaning they are standalone. That's why it's called independent variable. They are not influenced by one another. So you have to do so. Even if your bivariant logistic regression is significant, you have to test for confounders just to ensure that they are truly independent. So how do you do the multivariant? It is also very straightforward. So once you're done with the bivariant, all right, you come back to this analyze for the multivariant, your regression, but this time you go to multinomial logistic regression. Multinomial logistic regression. Then you still select your dependents, which is your preventive practices, 1 and 0, you put it here. But you're going to be putting all the significant variables inside this pool at one time. The age, the marital status, educational level, all the variables that all the independent variables that are significant, you put them in the pool together for the multivariant, not like in the bivariant where it is one at a time. In the multivariant, you put everything together and that's all you do. You now say, okay. And you see, it's going to give you the same table, but this time all the tables are together. So you can see the gender is still significant. Male 12 point, female 1. Age group, all the age group, they have lower odds but significance. You can see. The marital status, these have lower odds, is not significant, but the other, this one is significant. So this is the bivariant. Everything you put them together, which is what I have done here. So I put everything together, and it will interest you to know that the variables that were significant in the bivariant are still significant in the multivariant, so that I can beat my chest and say gender is truly a predictor of level of preventive practices. Age is truly a predictor, meaning that from my adjusted odds ratio, the other one is crude odds ratio, the bivariant is called crude odds ratio, the multivariant is called adjusted odds ratio. From my adjusted odds ratios, you can see that males have higher odds of preventive practices than female. As you can see, male are 9.8 times more at odds of having good and adequate preventive practices compared to those that says others or female. All right, so this is how it works. If you look at the marital status, singles have higher odds than the married. So until you do your multivariant or adjusted odds ratio, you will not be able to say for sure if these independent variables are predictors of the preventive practices. So that's how the multivariant is done. And quickly in this second project, we looked at COVID-19 vaccines, public awareness, perception, acceptance. Why I showed you this is because I want to show you, apart from the descriptive statistics, before the bivariant and the multivariant, we did chi-square. So you can do that as well. So meaning that if you want to follow the process, sometimes after the descriptive, for the inferential statistics, you can do your chi-square. So our outcome here is the willingness to accept COVID-19. In this case, we have yes and a no. Our interest is in the yes. So meaning the yes will be the 1, the no will be the 0. This is our independent variables. So we are checking which of these demographic influence their willingness to accept COVID-19. So we did chi-square and p-value first. So you run your chi-square because you are checking for differences in proportion. After your chi-square, for the variables that are significant in the chi-square, you put them in your bivariate logistic regression, which is what we did here. Then the variables that are significant in the multivariate, in the bivariant, which is our model 1, we put them in the model 2, which is the adjusted. So you can see crude odds ratio, bivariant, adjusted odds ratio, which is model 2. That's the multivariant. So you can actually do it that way. Chi-square, significant chi-square, put in your crude odds, bivariant, significant crude, put in your adjusted. So you can also follow that format, which is also recommended. So for the chi-square, I also want to tell you something that I said initially. If you look at the gender, you will see that we tested differences in the percentages. All right? If males, if females, because you can see this is 75, this is 71, meaning that females have a higher willingness to accept COVID-19 than male, but 75 is not significantly higher than 71. So you see why the P is not significant. But look at this top one. We didn't use chi-square and p-value. We used what they call the Fisher's exact P, like I mentioned. Why? Because we have a 1, we have a 4. Anytime you have a value that is less than 5 in your association, you don't use a chi-square anymore. You use what they call the Fisher's exact P. It's a type of a p-value that adjusts for smaller numbers. You can see here too, we also use the Fisher's exact P because we have a 1 here. But in places where we don't have values that are less than 5, like marital status, no value less than 5, gender, no value less than 5, we used chi-square and p-value. So you can see that most of the social demographic were not significant. But the general factors, like if they have done COVID-19 tests before, if they have accepted the vaccination, they were all significant. So you can see from these, those that said they have done COVID-19 tests before had more willingness to take the vaccine, as you can see. 82% had more willingness to accept the vaccine because they have tested compared to those that have not. So you can see that having tested for COVID-19 makes them more susceptible and more willingness to accept. But now that we know our chi-square is significant, we now have to put this significant chi-square into our multivariant, into our bivariant so that we can see the odds. Our chi-square can only tell us that there's a proportional difference between 82.14 against 69.52, meaning those that have tested have a proportional, increase in willingness compared to those that have not tested. But it doesn't tell us the odds. That's why we have to move this chi-square value into the bivariance. So our bivariant now, which is the crude odds ratio, will now tell us that those that have tested, because 1 has to be your reference. So our reference is in the no here, which will now be the 0. Our yes will be the 1 in the case of the dichotomous. All right. So now in this case, our yes, which is the 1, our no, which is the 0, which is the reference, you can see that those that have tested are 2 times or 2.0 times more likely to receive the vaccine. So that's the difference between the chi-square and the odds. The chi-square only tells you a proportional difference. But when you step it further to do the bivariant now gives you the probability, which is a higher level than your chi-square. That's why when people run analysis and you end in chi-square, I don't usually recommend it. If you've done your chi-square, move ahead to bivariant. If you've done your bivariant, move ahead to multivariant so that we can test for confounders. Now, if you look at the model 1, which is the crude odds ratio, you can see that almost all these factors were significant in the crude. Interesting. Those that have tested for COVID-19 were more likely to willingness to test. Those that normally will accept the vaccination have a higher odds to test. Those that have positive perception of safety and effectiveness of the COVID-19 vaccine have higher odds to test compared to those that don't. But When we now moved all these significance into the multivariate to adjust for confounders, it's interesting to know that it was only those that have done the COVID-19 test that was significant. What does that tell you? All these other variables from normally will accept vaccination before to a perceived mean that COVID-19 vaccine for Africa is different. They were all tied to done COVID-19 test before. So meaning that if they have done the COVID-19 test before, was a stronger influence of all these other variables, meaning someone that have done the COVID-19 test before will most likely have accept vaccination before, will most likely have a positive perception, will most likely have a positive perception of the myth, a negative perception of the myth of COVID-19 vaccine. So you see why it's good to do the adjusted. Because if we didn't do the adjusted odds ratio, we would run around and be saying, oh, those that normally will accept the vaccination will have more willingness. But you have to understand that it is because the person have done the COVID-19 test before. That's why they will probably have the desire to accept the vaccination. You see why the adjusted odds ratio is good. So you see, all these other things were not significant anymore, meaning the main predictor of the willingness to accept COVID-19 vaccine for this study is the fact that they have done COVID-19 tests before. That gave them the strength to actually have the willingness to accept the COVID-19 vaccine. So I think this is where we're going to be wrapping up this session. Finally, there are many statistical softwares. Although I used the SPSS, we have EpiInfo, Power BI, Stata, SQL, Access, and the rest of them. So finally, before we go, how did I do the chi-square? I will show you that. Apart from the bivariant and the multivariant, this is how chi-square is done. So let's do chi-square between gender and our outcome. So you go to analyze, you go to descriptive statistics, you go to analyze, you go to descriptive statistics, but this time you go to cross-tabulation. You select your cross-tabulation, and in that cross-tabulation, your role is the independent, while your column is the dependent. If you see here, it's the same thing. Look at it. In the chi-square, look at it. Your column is the dependent, which is the willingness to test. Your role, these are the rows. That's your independent variables are the rows. All right? But the column is your dependent. So in the SPSS, you put your dependent variable in the column. In this case, is our preventive practices, good or poor. We put it in the column. Then our independent variable like gender, like the position, the gender, the age group, all of them can be in the row. Then you have to choose the chi-square. You have to go to exact and, not exact, statistics, and you can choose your chi-square. Why are you doing chi-square? Because you want to check for differences in percentages. That's why you're doing chi-square. So you choose your chi-square, you continue, then you have to choose your percentages. You're doing row percentages because the left and right has to be 100%. See what is happening here? 70 and 29, 100%. So if you have a dependent outcome where the yes and the no is inside that dependent outcome, you do row percentages. But if it is two different populations like rural, urban, when you're using two independent population, you do column percentages where up and down is 100%. But if the two values are in that dependent variable, you are going to do row, left and right 100%. So that's why in this case, you choose row percentage, not column, because left and right has to total 100%. You continue, and that's it. You say, okay. So this is our chi-square. So you can see the row percentage here, the good practice, the poor practice for Both staff and student, good practice, 95, poor practice, 4.6, 100%. So if you go down, you will now see your Pearson's chi-square, 2.18. You see your asymptomatic significance p-value, 0.534. So that's how I did the chi-square, and that's how I did my p-value. So I think that is it for this session. So thank you. We have rounded up the session. All right. So, okay. I didn't really get the part you said about using Fisher's exact value. So like I said, if I go back to that data, which is this one, I'm going to expand it. You can see that once you are doing a comparison of percentages, you're using the chi-square and the p-value. But that comparison you're doing, the frequency, the number of counts has to be greater than 5. So 119 is greater than 5, 96 is greater than 5, 47 is greater than 5, 32 is greater than 5. So because they are greater than 5, you are allowed to use chi-square, which is 0.25, and the p-value, which is 0.615, although it's not statistically significant, meaning that we can say that there is no significant association between gender and willingness to accept COVID-19. Both male and female is the same. As you can see, 71.69 and 75.0, no much difference. But in a case where a value is less than 5, like for age group, you can see 50 to 64. Like you can see for age group, 50 to 64. Those that said no, you have 4. 65 and above, you have 1. These values are less than 5. Once you have a value that is less than 5, in that association you're doing, you're going to be using Fisher's exact P. So if you notice there's no chi-square here, you only have a P and a symbol. This symbol down in my key in the main paper, this symbol is Fisher's exact. To tell you that I use the Fisher's exact for age because I have a value less than 5. I use the Fisher's exact for highest educational level because I have a 1, which is less than 5. But others that have values grade 5 and above, I used chi-square and I use the p-value. All right, I think that is it for the presentation. We have overshot our time, but I wanted to cover this and I wanted to show you the practical demonstration, so that it won't just be theory, theory, and theory. So thank you very much. We can have a few minutes for question and answer. I'm allowing you to unmute yourself so that you can ask your question. Let's see how many questions we can take before we go. So we have Adamu raising his hands first. Adamu, please go ahead, ask your question.
Okay. Thank you for the presentation. I would like to say it's an eye opener for me because I'm young in data analysis. So before my question, I would like to request for the slide at the end of the day, then as well as the auto aid data group.
Yeah.
I'm only in the general group. So I just have mine is just a clarification on the first work. That is the table 5 and table 6.
Okay, can I share it? Would that be okay? So that you would use it to.
Okay, you can share it. You can share it so that I will highlight my question from the slide.
Okay, so just a second, let me share it. So I should go back.
Oh yes, this is table 7, table 5.
Okay, hold on. Okay, this one, right?
Yes, this one. So for
sorry. Let me go back. This one, right?
Yes,
Good.
Okay, and my first question is the level of preventive practices.
Yes.
Where the number for good and adequate is 5486. Why the number for poor is 363 rather. So yes. I'm confused. Why is the variation from the good and poor? Because I think from the previous one, our general number is 5849. So I'm confused.
General number is what?
It's 55849. Okay, from your course. Okay.
Is the addition of good and poor.
Okay, it's the addition of good and poor. Then okay.
You've splitted the number into two groups.
Yes, I now get it. Then my second question is, what warrant us to do multi-voided variable in terms of
Yes.
data?
Yes, like I said, doing multivariants helps you to remove confounding variables because it can be tricky. And that's why I had to bring in this study because it displayed it very well. Now, look at the bivariant here. Done COVID-19 tests before. So those that have done COVID-19 tests before are more willing, right? You can see they are 2 times more. Those that will normally accept the vaccination are more willing.
Yes.
Those that have a positive perception of the safety and effectiveness of the vaccine are more willing.
Yes.
Those that have the perceived myth that COVID-19 has a tracking device, they are not more willing. As you can see, the odds now dropped.
Yes.
All those that have perceived myths that there's a tracking device in the vaccine, they didn't take, means they have a lower odds for willing to take. The same thing, those that perceive that it will alter your human DNA, lower odds. You can see there are lower odds for the negativity. But after adjusting for confounders, it is only the first one that was significant.
Yes, 0.03.
What is that telling you? It tells you that normally will accept vaccination before is tied to if they have tested for COVID-19 before. So meaning that if someone have tested for COVID-19 before,
yes,
it means that that will be influencing the second question. If they have tested or not tested for COVID-19 vaccine will be influencing. So whether they test for COVID-19 or not, that is what is influencing all these other things. Meaning that all these other variables are not standing on their own. They are not independent. That is what the multivariant is showing. But if we stopped at the bivariant, you will say, oh, all these other variables are predictors of willingness. But from the multivariant, you can now see it's only the first that is a true predictor of willingness. All these other ones, they are attached to the first. They are not true predictors.
Okay.
Meaning they are confounding variable, meaning they are hanging on to one another. They are not truly independent. You know,
okay.
they are all hanging on to this first guy here, whether they've done the test or not. Yeah. So that's why you need to do the multivariant so that you can take out confounding variables and have a true predictor.
Okay, sir. And okay, sir, my last question. I have a work that I would like to publish. So you mind sending me your mail so that I'll just forward the work for you maybe.
My email is in the slide. So I'm going to drop the email here now, but I know it's in the slide. And if you registered for the program, I would use the email address, you know, that you used to register and send the recording and the slide to everyone. But this is my email. You can copy it. In case you didn't hear from me, you can chat me up on WhatsApp or send me an email that you've not gotten the recording and you've not gotten the slide. Okay, so this is it. All right. So Ezenwale, please ask your question.
Okay, good afternoon. Can you hear me?
Yes, I can hear you loud and clear.
Thank you, sir. Emeka, thank you so much for this. I love the enthusiasm in your voice and the way you thought. I have a question around your sampling, when you were explaining around sampling methods.
Mm-hmm. All right.
Most of your words were directed towards random sampling. So I was like, does it mean that no matter the sampling method I use, it still narrows down to random sampling? Because you mentioned that even after stratifying, I have to go
Yeah.
back and use random to pick. Even after
Yes.
clustering, I have to go back and use. So I now made a statement. Does it mean that primary random sampling is like actually a primary sampling method?
Yes, it's actually a primary sampling method. Whether you do stratified or cluster, you still end up using random to pick the participant. What cluster does is to separate it into two, so that you can pick the participant. What stratified does is to separate and give you two equal groups so that you can randomly pick from both. What cluster does is to randomly pick the number of clusters so that you don't have to sample all the cluster. So that's why you would see, if you're doing stratified, it may likely be two-stage. The first stage is stratified, the second stage is random. The same thing with cluster. Sometimes you can do multi-stage, where you can even use all of this. You can use cluster, stratified, and random. How? You use a cluster to pick the school. You use stratified to separate the female students and the male students. And you use random to randomly pick each of the participants. So sometimes you can do multi-stage when it's more than two-stage, yes. At the end of the day, you still end up random sampling, yes.
All right, thank you so much. Thank you so much.
Thank you. Yeah, so because of our time, I'm sorry, maybe I can take one more question, then we can continue in the AutoAid hub, because our time is fast spent, so that we can wrap up the session. So one more question, then we can wrap up. So so if you can just wait a second, I would drop the link for the AutoAid hub so that you can actually, use this link to join the hub. But I will try and send the link by email to everyone that registered. But I'm dropping the link. This is the WhatsApp group link. So once you click that link, it will take you into the AutoAid Data Science Hub. So thank you so much, everyone, for joining this session, and I hope you enjoyed the session. So the slide has my contact details. We can always talk offline. So thank you very much. I hope you have a wonderful day today. Thank you. And
thank you.
All right, and take care. Bye-bye.
Thank you very much, Doug.
Thank you. All right, bye.
Thank you, sir.
Thank you.